What's up, everybody? It's Calc time with Miss Wesley. Today is just huge. Today we move on to the middle of chapter 4 where we start to take our indefinite integrals with those plus c's and make them definite. So this is our new definite integrals packet where we'll pull the examples for today and the coming week. We are on the first page of it, and we're going to start today talking about some area, but area that you haven't calculated before in previous math classes. Not area of simple shapes like triangles and circles and rectangles and trapezoids. We're talking about area under curves of functions, and calculus comes to the rescue. So I see that even Squidward is on this page, and he is jumping for joy. It's a rare time, a rare moment of happiness for a guy like Squidward. So I thought that I would start with a joke or two about, or a SpongeBob joke. So the joke is, I don't want to mess this up. Why did Mr. Krabs not give any money to charity? Because he's a shellfish penny pincher. And what did SpongeBob say to the Krabby Patty? Pleased to eat you. Because Krabby Patties, so good. Warm-up time. It says give an estimate for the area between x equals 0 and x equals 1 bounded by the function f of x equals x squared and the x-axis. So weird looking directions, but what's not weird are these equations and expressions. I know what x equals 0 looks like. I'm just going to put a dot right at the origins, this whole line here. I know what x equals 1 looks like, and I actually want to spread this graph out. I want to graph x equals 1 way over here. So I'll go 0 to 1. Bounded by this line and that line. So the x equals 0 is already there. It's the axis. Maybe I could get a line drawing tool here. And x equals 1 should be about here. So now we've got our horizontal boundaries for the question, and it says bounded by the function f of x equals x squared. I want you to think about what that would look like. Y equals x squared is a normal parabola that opens up. I've plopped on the y-axis all the way at the top, y equals 1 unit. If you plug in a couple easy points, like x, if you square 0, you get 0 back. If you square 1, you're going to get 1 back. You have a point at 1, 1. You have a parabola that goes through them from there. I want you to do your best to make this look like a nice smooth curve. Mine's not going to look perfect, but you have this parabola that opens up. And really, it doesn't matter what I did in quadrant 2, because I care about the area from 0 to 1. I want to shade it in here. So it's bounded by x equals 0 and x equals 1. The curve, y equals x squared, and the x-axis. So I want you to guess, what do you think that area is in square units? Well, this entire box here is 1 square unit of area, so it's definitely less than 1 and more than 0. It looks like it's slightly lower than a half of a square unit, because a half of a square unit would be all the way diagonal, yikes, this way. So I'm going to guess maybe 0.4, maybe 0.3 or 0.35, maybe even 0.25. All these square units might be good guesses for how much area, how much space that shading takes up. Now you think to yourself, what could be a better way to do this calculation and not to have to guess? Well, I got to think. If I'm talking about the same area in all of this space down at the bottom of the page, what would be a better way to calculate it? And I got to think of one of the shapes, one of the geometric shapes that has the most easy to handle area formula. And the winner is going to be a rectangle. Rectangular area, super easy to calculate, length times width of each of those rectangles. So what I want to do is, if you want to pause the video, I'm going to pause as well. And I'm going to draw the same picture we did for the warm-up, the rough picture, in for these next 3 drawings, just without the shading. So I'll pause and then show you what I mean. So I just went down the page and gave myself that same rough sketch of the shaded area that we care about for these 3 approximations. It says we're going to divide the region in question, this region here, into 4 rectangular regions, make 4 skinny rectangles, then approximate by adding the areas of those rectangles. And here's how I'm going to make them. One actually isn't even a rectangle at all. We're going to use left-hand endpoints for starters. And what I mean by left-hand endpoints, I mean the left hand is going to touch a point on the curve. And I want to split this up into 4 equal parts. If you have room to label it, you're going over a quarter, so 0.25, 0.5, and then 0.75. You're splitting up 1 unit into 4 quarters. The first rectangle, like I was kind of hinting at, isn't actually a rectangle at all. its height is 0. It just comes up and hits that left-hand intersection point with the curve. The next one, though, is just going to be this slightly taller rectangle that comes up and hits the curve when x equals 0.25. Where's the curve when x equals 0.5? It's here. I've got a third rectangle to draw. And then lastly, my last left-hand endpoint is at 0.75, and you see this rectangle that's there. What we're going to do is, because it's simple to find the area of 4 rectangles and just add them up, for the sake of argument, we're going to try that now and get an approximation. See how far our estimate from the last part of the problem was off from the real solution. Well, you'll notice you can predict right now that adding the area of these 4 shapes is going to be an underestimate. You notice there's that little chunk of missing space that's not going to be accounted for. We'll see if we can remedy that in the next couple. But let's see, area equals, it's got to be length times width. Well, let's make this shorter for ourselves. Doesn't each of these rectangles have the same width? The width is always 0.25 for all 4 of those structures. So I'm going to put the 0.25 outside of parentheses, the width. And then what I'm going to do is inside of brackets, I'm going to add up all the heights. In our graph, how do we get the heights? We're going to find out where each of these x values intersects with the curve. So here's how it looks. I'll write it and then explain a little bit better. It's f of the first left-hand endpoint would be the first height, so f of 0. F of, if you go a quarter over from that, it's f of 0.25. You're like adding a quarter to the x values. F of 0.5 and f of 0.75. These represent the heights of 4 quote-unquote rectangles that hit y equals x squared at the left-hand endpoint of that rectangle too. So f of 0, how would I get that? Well, you're using y equals x squared. You're basically squaring each of these values, and I'll flip back and forth between looking at a calculator and trying to do some of this stuff in my head. So for instance, 0.25 stays on the outside, and f of 0, 0.25, f of 0 is 0 squared is just 0. If I square this one, right, f of 0.25 would be 0.25 squared. You plug into the original function, you get 0.0625 is the height of that rectangle here. What's the height of the next one? It would be 0.5 squared, so 0.25 would be the height of the third rectangle. And the height of the fourth rectangle is 0.75 squared, and that is 0.5625. Feel free to pause so you can do this calculation on your own. I'm going to write what the calculator gave me. It gave me exactly 0.21875. Now I said exactly, but this is just an estimate. We'll put square units on it because we're talking about an area approximation, and I would call this an underestimate. If I looked at the picture, I see that there's chunks of empty space that wasn't accounted for. So I want to, like I said, fix that. We're going to try right-hand endpoints next. So let's see, let me just slide myself in the middle here. Using right-hand endpoints, we'll draw the picture just so that we get a visualization of how this should probably be an overestimate. So I will split this up into 4 equal parts. So 0.25, 0.5, and 0.75. And you're always using right-hand endpoints. I'm going to go from right to left. Here's a right-hand endpoint of the first rectangle. So it's nice and tall, and it is an overestimate of the area under that curve. Next, right-hand endpoint comes over to here, another overestimate. Next, right-hand endpoint, you're just hitting it on the right top corner of that rectangle on the curve. And the last one is a slight overestimate as well. Slide that right back on there. And you're going to add those 4 areas together, the areas of those 4 rectangles. So let's give that a try and see if I can keep it a little bit neater here. Your width is the same. In this one, you still have 4 rectangles, and their width is a quarter each. So since we're doing length times width of each one, I'll take care of that by just putting a 0.25 on the outside. You want f of each right-hand endpoint, not left-hand, so you're not starting at 0 this time. Can you start at the first right-hand endpoint? So start at 0.25. So the height of the first rectangle, the height of the second rectangle, the height of the third rectangle, and this time our fourth one has a right endpoint of x equals 1. So this is the width times all the heights of the 4 rectangles added together. Well, this is 0.25. This is where I just used a calculator, squared each of these things. So we said 0.25 squared was 0.0625. 0.5 squared is 0.25. 0.75 squared we used in the last part of the problem, 0.5625, and then 1 squared. We shouldn't need much help for that. We can put a 1 at the end. Here is your overestimate. I went to the calculator for this, 0.46875. I'm already feeling better about my guesses from the warm-up because they were right around, a little below this, a little above that. We'll say units squared, since it's an area approximation. And this we can acknowledge from the picture is an overestimate. We're getting closer. Is there anything you would think to do next? I guess, let's say, okay, I have this using midpoints at the bottom of the page, but even just using these two values, could we get a better guess if we had to? Is anybody thinking to average them? That's what I was thinking. Maybe a better estimate would be to take the underestimate, take the overestimate, and average the two. So if I average the left hand and the right hand endpoints, we're getting closer and closer to the real solution. Average those two numbers, you get 0.34375 square units. And for this one question that we've been on for the whole page, this is the best that we've done so far. That's our best estimate, but it's not good enough. I want to do a tiny bit better. Lastly, if the left hand was too small of an estimate, if the right hand was too large of an estimate, what if we used midpoints of those rectangles hitting the curve y equals x squared so that every single rectangle was a little bit of an overestimate and a little bit of an underestimate, kind of counterbalancing the whole thing. All right, so let's try to draw this out. What we're going to do is we're still going to split this into 4 rectangles. So you're still going a quarter, a half, 0.25, 0.5, 0.75, and 1. But when you draw your rectangles, can you draw it so that the midpoint of the top of the rectangle intersects the curve y equals x squared? So this first rectangle that I just drew, it is both overestimating and underestimating at the same exact time because you have this little chunk up top that isn't accounted for, but a slightly bigger chunk above that is an overestimate. You've got that kind of counterbalance. Try the same thing here. Can you put the midpoint of the rectangle hitting where the curve is? You see that you've missed a little chunk to the right and you've gained a little extra piece to the left. Okay, here's another midpoint. It's both an over and an underestimate. And then the last midpoint's kind of hard to draw there. Did not do the best job. With the midpoints, watch me with the calculation. You've still got, each of these has a width of still 0.25 for your midpoints. Each of these heights of the rectangles is the midpoint. What's the midpoint between 0 and 0.25? It's half of 0.25, 0.125. Okay, next one. The midpoint between 0.25 and a half is going to be 0.375. We got 2 more. The midpoint between 0.5 and 0.75, you average those two numbers, you get 0.625. And lastly, the midpoint between 3/4 and 1, we would have 0.875. 0.875. This is a lot of calculating, and you can just trust me from here. We are not going to be doing this a lot. We're kind of just experimenting before we have an actual shortcut. So all these numbers would get squared. You'd add them up, multiply by 0.25. If you want to trust me on this one, you get an approximation of 0.328125. And I said that so far this was the best we could have done. Well, you know what? Now this is the best you can do with 4 rectangles. And look at the bottom. Look at the question that's asked. How could we make this process more accurate? I don't know if you were going nuts looking at all these calculations so far being like, this takes a really long time. There must be a better way to do it. We can make the process more accurate using more and more, I'll put in parentheses, skinnier rectangles. So let's finish this up with a note at the top of the next page. I bet before I turn there, wouldn't this process be more accurate if instead of 4 rectangles, I used 8 rectangles and they were all skinnier, right? You're overcounting and undercounting a little bit less. What if I used 100 rectangles or 1,000,000 rectangles? Well, that makes me think that we've come full circle. I feel like in the very beginning of the year in calculus, we were talking about limits. As n gets bigger and bigger and bigger, go ahead and flip the page. You turn to the next page and you see this picture here. The limit as n, the number of subintervals or the number of rectangles goes to infinity, is going to be the actual solution of the area under the curve. You can fill this in here, limit of sums. and I am going to leave you in suspense. We'll kind of join up at the very next part back on this page, and I'll give you some shortcuts for how we're going to do all of this. Enjoy your day. See you later.